Dear students, welcome back to another session of architecture and programming models for GPUs and coprocessors. We're currently in part 3, which is called the graphics pipeline. And last time we started talking about graphics APIs. We talked about immediate mode APIs and about retained mode APIs. And we started a discussion of the OpenGL graphics API. We're not rigorously learning OpenGL, but we're learning OpenGL to an extent so that we understand how traditional graphics APIs work and how traditional graphics APIs would match with current graphics architectures. So with graphics processors, this here is the situation that we're in. We're in a situation where we on the one hand have like a host computer, and then we have a graphics coprocessor, and the graphics coprocessor basically is the interface between the host computer and the display. And with a traditional data model, what would happen is that the host system would issue so-called commands to the graphics coprocessor, and the graphics coprocessor would handle those commands. Like for instance, the host would issue copy commands, and the graphics coprocessor would have like a context object, like where it stores its state, and would keep book where certain buffers in memory go, and would keep book which buffers are filled with data. And a copy command, for instance, would like modify a buffer in the graphics coprocessor's context object. And the host system would be able to specify other commands, like for instance, commands that change the state, like for instance, commands that change the current lighting setup or the current material setup, or a state change that binds another shader or another clip plane. And then finally, there are also, of course, draw commands. Like in those draw commands, they would cause the graphics coprocessor to basically flush its output to the display. So you can already see that this is a model that is pretty much a one-way street, right? Like the host system issues commands, the graphics coprocessor like buffers those commands to some sorts, and the graphics coprocessor translates those commands into state changes and has a global context object. And then, like when a draw command is issued, then at some point in time, like this usually doesn't happen right away, but there's usually a bit of a delay. The graphics coprocessor causes the output to be displayed. Like we have a data flow that like strictly goes from left to right, where the host system issues commands, the graphics coprocessor processes those commands, and eventually will tell the display adapter to display the rendered image. And this is a very traditional model, in that we assume that there is only ever like one host process. And things become so much more complicated when we have like multiple processes on the host that can concurrently issue commands, because then the graphics coprocessor like needs to maintain the state differently. Like we don't get away with a global state object anymore, but we have like multiple states, like maybe multiple states per application or even per thread. And that's of course makes things more complicated, because the host and the graphics coprocessor need to keep in sync about where data copies go. Like when a command is issued, then the graphics coprocessor needs to disambiguate which context is responsible for storing the outcome of the command. And also when the host issues a draw command, it's then important to synchronize which context is currently active and which context is associated with the draw call. So this doesn't mean that it is necessarily impossible to implement such a design, but what I'm mostly trying to convey here is that those large heavyweight context objects don't bode very well with typical multi-process, multi-user scenarios, where we have like different processes and different threads that simultaneously access the GPU and simultaneously issue draw commands. And this is the setting that we're currently in, and we're currently discussing OpenGL as a typical immediate mode programming API that under the hood maintains a context object that maintains the whole device-side graphics state of the application. So in our approach of discussing all this in the context of a traditional graphics API like OpenGL also has the advantage that we are able to, like, on the fly, learn certain terminology and learn certain concepts. Like, this is what this part of the lecture is actually about. Like, we're not really learning OpenGL, but we're learning concepts and terminology of a typical graphics API. And those concepts and terminology, for instance, include contexts, resource handles, shader programs, and what's important here is that we understand conceptually what they're there for and why they are or why they were preferred to certain other typical language or API constructs that also might have come to use. Like a typical example are, for instance, resource handles. And resource handles are used on the GPU as basically as an alternative to pointers. And this is very typical for GPUs that the typical graphics APIs like OpenGL don't allow us to directly access memory, but they instead provide us with resources, and those resources can be accessed via handles. Like a handle can be thought of as like an integer or like an enumerator, and like, for instance, the integer might identify a buffer. And like per convention, for instance, when the handle is 0, that means that we have a invalid buffer handle, and otherwise we'll just have a positive integer that goes from 1 to the number of buffers that there are. And this is mostly due to the fact that memory on GPUs is much more heterogeneous than it is, for instance, typically on a CPU. Like on a GPU, we typically have like memory regions that are responsible for textures, memory regions that have to do with the frame buffer, and memory regions where general buffers or vertices go. And therefore, we usually don't like directly access memory via pointers. Like, there's a notable exception is, for instance, the CUDA API that we will also learn about during the lecture, where you actually have access to device set memory using pointers, but usually you don't have that, but instead you have resource handles, and you can access like those resources via their role. Like, you don't really access memory, and access the memory with the knowledge that this certain region of memory stores a buffer, but instead you directly access a buffer via its resource handle. And when we were talking about contexts, then those contexts can mostly be thought of as storing resource handles. Like, there are huge storage objects that we communicate with via resource handles. And this is also one of the reasons why resource sharing between threads is so heavyweight, because we usually have a limited number of resources that is available per graphics application or for a graphics thread. And sharing those resources is really not just accessing a certain memory region via a pointer, but usually would see us obtain a handle to a certain buffer, bind that buffer in our context so that we have exclusive access to that. And the operations that are concerned with that are usually actually quite heavyweight. We already said that GPUs usually implement the rasterization algorithm. And like in the early days, we just couldn't modify how the rasterization algorithm was called. So what we would do is we would have set up our vertex buffers and our normal buffers and other like array buffers, and then we would bind them, and we would just call GL draw buffer, and then like OpenGL would draw what's in the buffer and would draw it maybe to the current back buffer, and we have configured a double buffering context. It would just draw to the back buffer, and then under the hood the rasterization algorithm would be executed, and we wouldn't have much control over how the rasterization algorithm would be executed. Like, there was like a common lighting model that was used, and we only could influence that via configuration. So we could set certain parameters, like we could, for instance, set light colors or material colors, but we couldn't like influence the fundamental way how the shaded color was created with the rasterization algorithm. And then, like, when we issued certain draw commands, we would in the end tell the GPU or the graphics processor to actually present the image. And this usually happens, like this usually actually happens with operating system calls that interact with the OpenGL, and we usually cannot do this via the graphics API directly. But we would usually use a function like this GLX swap buffers, and Windows and macOS have similar functions for that. So we would instruct OpenGL to swap the front and back buffers and therefore display the image. Like we have this immediate style API where we have draw calls like GL draw buffers, or like with even older versions of the API where we just call GL begin, GL end, and then like GL vertex in between in order to draw graphics primitives. But then on the other hand, the API acknowledges, even though it is like immediate, it acknowledges that commands aren't like executed right away, but they're instead buffered and will only be retired eventually. Like all those commands like finish, flush, or swap buffers, they won't come with a timing guarantee, but the only thing that they do is they basically synchronize the graphics pipeline. And the presence of those commands, of course, also acknowledges that the interface between host CPU, graphics processor, and eventually between the display is asynchronous. Like whenever we issue a draw command, then the actual execution model will not be immediate. And even when we directly instruct the GPU to finish execution and to flush its output, even then there is no guarantee that we will immediately see an image, but that will only cause the GPU to know that we will eventually want to see an image. So we have on the one hand a immediate mode API, and on the other hand we have an execution model that is asynchronous, and we have the API acknowledging that by providing certain function calls and by shifting more and more from immediate mode execution to a buffered and asynchronous execution model. We will now have a relatively detailed discussion of shader programs, and you will recall that we already discussed shader programs briefly when we talked about the deferred shading algorithm in the computer graphics part of the lecture. And we already know that shader programs are there to influence the execution of the rasterization algorithm that runs on the GPU. And we know that shader programs are directly dispatched on the GPU, and that they run on the GPU, and that they influence like how vertices are transformed and how fragments are shaded. And for that, we'll consider the formulation of the throughput optimized rasterization algorithm, so of what we call the rasterization algorithm 2. And we recall that we have this vertex stage, like we have a parallel loop over all the vertices, and inside that loop we have the vertex shader execution. So this is the one entry point where a shader is being executed. And then we have like what I call primitive assembly, where triangles are set up and converted to edge equations, and those edge equations are passed to the raster engines, and the raster engines compute scan conversion and use the Pineda algorithm for that, and the output from scan conversion are fragments. And then we have a parallel loop over all the fragments that will execute the fragment shader. So this is our next most important entry point for our shader programs. And this is followed by this bottleneck basically that caused our algorithm to be CRCW, where we perform the depth test and the alpha blending test, and where we also need this guarantee that fragments are in the same order as the triangles that were specified by the user as input triangles. And shader programs, which are executed at those entry points, they are like they're like C programs, like the typical shading languages that come to use usually adopt features from C. Like they're usually different in that they extend the language. And we have like the aforementioned vertex and fragment shaders, and the vertex shaders are mostly there in order to like implement custom transformations. Like, for instance, in the vertex shader, we can influence the vertex color, and we can also influence like certain vertex attributes. But we can also influence the vertex positions. So that allows us to arbitrarily transform the vertex. And in the rasterization pipeline, the data that is processed and that is eventually output by the Vertex Shader then goes through the raster engines and through the scan conversion phase, and there it is being interpolated. Every vertex attribute is then interpolated across the triangle. We will learn a bit more about raster engines later, and we will see how this interpolation phase, how this is being executed. But what's important to note is that the Vertex Shader execution is followed by a rasterization or by a scan conversion phase, and the scan conversion phase causes the vertex attributes to be interpolated. So when the Fragment Shader then operates on the fragments, we actually have access to the output from the Vertex Shader in its interpolated form. And the Fragment Shader can also modify the fragment, it can modify the fragment's color. It can actually also modify other things like the fragment's depth. It can actually even discard fragments, exclude fragments from the ensuing raster output phases. And we'll also talk about this later, because this also has certain implications to how the pipeline executes. And apart from those two arguably most important shaders, like the Vertex Shader and the Fragment Shader are the shaders that we will concentrate on, there are also other shaders. For instance, there's the so-called Geometry Shader. And the Geometry Shader is executed after the vertex stage. The vertex stage will only ever be able to influence the behavior or the positions or the colors that are associated with input vertices. And the Vertex Shader is, for instance, not able to discard vertices or to generate new vertices. So at some point in time, the vendors actually added geometry shaders as a means to emit new vertices from the GPU, to emit new geometry from the GPU. And this obviously has the advantage that we don't have to go through the host system and through PCI Express in order to generate new geometry. On the other hand, geometry shaders are there are certain rather severe restrictions to this shader type, and the fact that we emit more geometry dynamically on the GPU also doesn't lend itself very well to typical GPU execution models. We're usually in a very streamlined execution model that runs over all the vertices, and the geometry shader usually causes the pipeline execution to become more complicated and is quite often very ill supported by the vendors. So the geometry shader is there, and we can use it to emit more geometry if we want to, but suffice it to say that this stage is often not very well supported by the vendors, and often it is actually not very fast to use. Depending on the driver and on the GPU model that we're using, geometry shaders are actually not very fast to execute, and therefore we will not concentrate so much on geometry shaders. There are optionally, there are also tessellation shaders, which are a bit similar to geometry shaders in that they create new geometry. But the way that the tessellation shader creates new geometry follows certain rules. The geometry is created by means of certain subdivision surface algorithms, or by using the input geometry as a control mesh and computing Bezier patches over that control mesh, etc. And this type of shader can also help to generate more geometry dynamically on the GPU. And in particular, it can help to make meshes that are relatively coarse more smooth programmatically on the GPU. And this is actually also a kind of a very special purpose shader type. So the shader type is there, but its use cases are actually quite limited. So we'll, in the following, concentrate on what I personally find the more important shader types are the Vertex Shader and the Fragment Shader. There are actually also more shaders, like NVIDIA very recently introduced something which is called a mesh shader, which has a very similar execution model to the compute model of the GPU, where you actually have access to multiple threads, and those threads would execute not only on a single vertex, but on a group of vertices at once that form a so-called meshlet. The execution model, as a matter of fact, actually better matches how GPU architectures are implemented nowadays. But as they are like a very vendor-specific shader model, we'll also not discuss mesh shaders in detail here. There are also other shaders, like, for instance, shaders that deal with sampling and anti-aliasing, and there's also something that is called a compute shader. And we will not talk about compute shaders in this lecture. We will instead discuss the CUDA programming model during one of the later sessions, which is can be thought of as an alternative to the compute shader pipeline that is compatible with like Vulkan or OpenGL. In regards to terminology, that actually differs a bit across APIs. So you will already have noticed that I was referring to so-called shader programs, and that I was also referring to so-called shaders. And the terminology I'm adopting here is one where the whole collection of shaders is a shader program. So the Vertex and the Fragment Shader and potential other shaders together form the shader program. So we have a model where shaders are compiled and the program is linked from those individual shaders. So this is actually the terminology that OpenGL uses. And we're going to adopt this terminology, but note that other APIs, like for instance Direct3D, might have a slightly different terminology, in particular where like what I call a shader might be called a shader program, etc. Also note that certain APIs, and in particular Direct3D, calls what I call a fragment shader. Those APIs would call that a pixel shader. So the terminology differs a bit depending on the API that you use, and we will mostly adopt the terminology that is used by OpenGL. So in the following are the more notable representatives of the family of shading languages. Like front and foremost for us, there's GLSL, sometimes called GLSlang, which is the standardized shading language that comes with OpenGL. And it is important to note that originally OpenGL didn't have a shading language. Like originally, GPUs didn't allow for programmable stages of the rasterization algorithms, and shading languages were introduced using extensions. Like the GLR fragment program extension allowed for like assembly language-like modification of the fragment stage, which was actually very limited, which for instance didn't allow for dynamic branching, etc. And then Microsoft introduced shading languages with DirectX and Direct3D, and they cooperated with NVIDIA, and they together developed the shading language called HLSL, and NVIDIA called the same thing CG, and CG is by now deprecated and no longer actively maintained, but CG could also interoperate with GLSL, so that basically brought shading languages into OpenGL, and then later there came GLSL as the standardized form that is widely used nowadays. There are also like API-independent languages, like for instance the Open Shading language, which is a language that doesn't serve as an extension to like OpenGL or DirectX, but rather as an independent shading language that, for instance, people can use in their own applications. Like when you write a ray tracer or in general a rendering application, then you can use an Open Shading language as a language to perform modifications that influence how materials look, etc. And there are also very specific languages, like that are very specific to APIs, like for instance Pixar's RenderMan as its own shading language. So there are like a bunch of different shading languages. What we at least can say is that at least on GLSL and HLSL they are quite similar. Like HLSL is undergoing certain developments. Like there are certain features, for instance from C++, that are going into the HLSL specification or standard, while GLSL doesn't have all those language features, but nevertheless their models are relatively similar, so it's kind of okay for us to just learn one language and then we basically understand how the other languages conceptually work. And what is important to note about those languages is like that they have a highly parallel execution model. That is, the shaders basically operate on single instances, and they have little to no access to other shader instances. Like when we have a vertex shader, the vertex shader is bound to a single vertex instance, and we have no means to actually access like other vertices that are operated on at the same time. And the same is true for fragments. Like when we have a fragment shader instance, that fragment shader instance is executed for a single fragment, and we have no way of accessing other fragments from in there. So the execution model is highly parallel. And it is important to note that this doesn't necessarily match how GPUs work nowadays. Like we already learned that GPUs work on so-called fragment quads. So, and we cannot, can only implicitly access the fragment quad from within a fragment shader, in that we know the derivatives there, but we cannot just access the neighbors. And it is also important to note that the general execution model of the GPU nowadays is quite a bit different than the execution model that is implied by shaders. Like usually on the GPU we have a execution model, and we'll learn about that in much more depth later, but the execution model usually uses something that is based on thread groups, and those thread groups, they operate together like in conjunction, and they operate on a certain collective workload, and this doesn't necessarily match with the shader execution models. And this is one reason why NVIDIA introduced the so-called mesh shaders that are a much better match to the execution model of a GPU. All those are things that we will discuss in more depth in due time. But it's still important to note that there is this highly parallel shader execution model, and the execution model allows for very little access to neighboring instances of vertices or fragments. And it's also important to at least note that this is not necessarily how GPUs work nowadays. So, and apart from that, we are now going to focus our discussion on both vertex shaders and on fragment shaders. And on a side note, OpenGL requires that there is at least a vertex shader. Like for a modern OpenGL program to be valid, there needs to be a vertex shader. And if we want to display an image, if we want to render an image, then we also need a fragment shader in order for the OpenGL application to be valid. Like in certain cases, you might have an OpenGL application whose output is not necessarily an image. So it is okay to not have a fragment shader, but it's important to note that without a fragment shader we won't see anything. And without having a vertex shader, it's undefined behavior. There's also what is called a compute pipeline to OpenGL, where things are a bit different. But the compute pipeline we're going to ignore in this lecture. So, and with that, we can now have a look at our first shader program and at the very first shader instances. So this here would be like the most simple imaginable vertex shader in a typical rasterization-based rendering pipeline. The notation I'm adopting here is based on GLSL. Like there are some minor differences maybe to certain GLSL versions, and there are also certain keywords and how those keywords are used that is slightly different from version to version, but it's close enough to what a GLSL program would look like. And I'm actually quite confident that it would actually compile depending on the version that you're compiling with. And what you can see is I'm modifying the position here in the GLSL program. Like the vertex shader is running for every input vertex, and then I'm just setting a position, and the position is based on an input attribute that is the incoming position, and then I'm homogenizing the coordinate of that position. That is, I'm adding a W coordinate and giving it the value 1.0 to indicate it's a position in space. And then I'm using those two 4x4 matrices, and those two 4x4 matrices, they actually also come in from the application, so the application passes them in as an input parameter, and I just multiply them by that, and that gives me the vertex output position. And we already said that in OpenGL it is mandatory to at least have a vertex shader, and this would basically be the fallback vertex shader, assuming that we have a camera matrix. Things could actually be simpler, for instance, if we wanted to render a view-aligned geometry, then things would actually be a bit simpler. Like, we would assume that the camera transformation wouldn't change over time. But in general, this is like the simplest imaginable vertex shader. Like, we're writing out the position of our vertex, and then we have access to certain input attributes. So the first distinction that we have to make about those attributes is if they are like global attributes or if they are per vertex attributes. Like the position here, like the incoming position, is a attribute that is relevant only to this one vertex. And then there are other attributes, like the ones that I'm marking as in attributes here, that are global in that they have the same value across all shader instances. Like the attributes that are associated with the vertices, they vary with each vertex, and they usually come from some type of buffer that was like initialized on the host. And in the buffer, there's in general a different value for each vertex. And then we have certain attributes that are sometimes also called like uniform attributes. And those uniform attributes, they are global and they are the same for all shader instances. Like typical examples of those are the camera matrices that are the same for vertices. Or like here in the example, for instance, I'm animating the position of the vertices. That is, I'm making them like undulate a bit by passing in the current time, and the time would be initialized on the CPU. So the CPU would use like a timer or a timestamp, and would transform that into a floating point variable and pass that as a uniform variable into the shader. And the shader instances would all have the same time value available, and then they would animate their vertex positions a bit. Like this here would basically have the positions undulate. And then we would again perform those transformations. Like this shows it like a typical example of what one would do in a vertex shader. Like for instance, if you're rendering an ocean surface and the ocean is in motion, like then you would like one option would be to just perform the whole computation on the CPU and then for each frame re-upload all the vertices. But we have that very specific knowledge that the vertices, that at least the number of vertices will always stay the same. So and this fits very well with our vertex shader model because we won't emit any new vertices here and we also won't discard any vertices. And we also know that their connectivity stays the same. So the vertices will retain their relative position in the mesh, like with regards to its neighboring vertices, so all that won't change. The only thing that changes here is like their relative position, like maybe we're changing the altitude of the vertex a bit. And this is the only thing that changes, and this is a typical animation that one would use a vertex shader for. So in order to avoid a potentially costly, high bandwidth and high latency communication over PCI Express. So now we discussed and we've understood those user-defined global attributes, and there are also user-defined per vertex attributes, like the position we already saw, but the user can also like pass in normals and other things, and those user-defined per vertex attributes, they would usually be passed in using a buffer. Like in this case, we would have a position buffer, like which would go into our VBO, into the vertex buffer object. And then we would have a additional array buffer which would contain the normals. And you can also see that there are like certain outputs from the vertex shader, like the normal output, that are predefined. So certain outputs are predefined and can be modified within the vertex shader. And the notable examples of those are the vertex positions, the vertex normals, texture coordinates, and like usually graphics APIs allow for multi-textures, and therefore we would have like not only one texture coordinate, but a bunch of them. And those can be modified from within the vertex shader. But GLSL also allows us to modify user-defined attributes, like general user-defined attributes that aren't written to a standard output, but that are passed through the pipeline as real user attributes. And like when the output is processed by the ensuing part of the pipeline, Then the next thing that happens with the very simple rasterization algorithm variant that we discussed is that it is passed through the raster engines. Like in reality, there are some other stages like tessellation stages, geometry stages. We're ignoring those for now, but we're now assuming that the output from the Vertex Shader is directly passed through the raster engines. Like there's the primitive assembly phase, and we'll end up with edge equations, and those edge equations, they are passed through the raster engines. And when the Pineda algorithm is executed, we do this in 2D basically, and all the vertex attributes here are like attributes that are interpolated across the triangles. Like in this 2D coordinate system that the raster engines operate in, the depth, for instance, is an attribute, and we have with each vertex associated a depth. And then when the Pineda algorithm is executed, the algorithm uses barycentric interpolation to assign each fragment a depth value. And the same is true for normals. Like the algorithm will use barycentric interpolation to interpolate potential vertex normals that were specified by the user. And the same is also true for texture coordinates, like for UV coordinates, or also for other user-defined attributes. And that means on this way, from the vertex stage to the fragment stage, we have interpolation. And there is a certain attribute type that allows us to specify that we want to access an output from the vertex shader in its interpolated form from within the fragment shader. And this attribute type is called a varying variable. And like this keyword is actually deprecated by now. There are other keywords for this, but the concept here is that this is a variable that is passed from the vertex shader through the raster engines, and there it is subject to interpolation, and in its interpolated form is then available in the fragment shader. And so here's what a very simple fragment shader could look like. Like in this example, we are given like our varying input variables that come from the vertex shader, like the normal and the UV coordinate that were interpolated. And we also have a certain input that is specific to the fragment shader that we didn't use in the vertex shader, like for instance the light source direction or a diffuse texture. And like it's important to note that we're now implementing the whole fragment phases here. That is, we formerly had this for loop over all the light sources and would perform fragment operations per light source. And this would now be handled in the fragment shader. Like this simple fragment shader here assumes that there's really only one light source, and in general it's a viable assumption that there's like a constant number of light sources, and if there were more than one light source, our shader would have a loop where it would iterate over the number of light sources and then perform the calculations for each light source. But that loop is part of the fragment shader, and the fact that there are light sources and what the configuration for the light source is like an attribute to the fragment shader. So we have those input attributes like the texture and the light source, and we also have the attributes that are coming from the vertex shader that are interpolated. And then we're going to assign an output fragment color, like an RGBA color. And the fragment shader here is really like, it can also be thought of as the most simple possible fragment shader, in that it really only performs like Lambertian shading. Like there are of course even simpler models than that, but this is actually like one of the most simplest model that we can imagine. Like our fragment shader would access the 2D texture, and you can see that there are like special functions for this. So if I remember correctly, there are also like functions that are called like image 2D. So don't rely too much on the syntax here being perfectly exact. But what's important here is the concept, so that there are like dedicated functions that help us to access our texture through those sampler objects, and then we obtain our diffuse color, and then we basically compute ourselves the lighting model. That is, we define how the light direction and the normal together form a shaded color. Like in this very case here, we're basically just computing the dot product between the light direction and the normal, and then we cap that out so that it won't go below 0. And we know from the computer graphics sessions that this is actually only the Lambertian shading model, and this is a view-independent model. So if we were to compute like a Phong or blind Phong model, or even a more complicated model, we also would need a view direction, and that view direction would maybe come from a vertex shader, so things could be more complicated. But here they aren't, and then we're using that as a weight for the diffuse color that we looked up from the texture, and assigning that to the fragment color, right? And the fragment color is an RGBA color, but our surface is opaque, so we're setting the alpha component to 1. So what's important to note here is, like, inside a fragment shader, we can basically perform any computation to compute the fragment color. There are also certain other variables that we can influence from within the fragment shader that I'm not showing here for simplicity. Like, for instance, the fragment's depth could be influenced, the fragment could be discarded. But this is the concept of a fragment shader, that we assign the fragment color based on some more or less complicated computation. And what the computation is actually pretty much up to us, like how we compute the actual color and what the attributes are that are important for the computation. And yeah, I already said that newer APIs, they have usually more programmable pipeline stages, like there are geometry shaders, where the geometry shader is executed after the vertex pipeline, and the geometry shader is basically passed the vertex as an input and can use that vertex to generate more vertices. Like, the geometry shader will not just create geometry out of thin air, but it requires as an input an additional vertex. Like, what people, for instance, commonly use vertex geometry shaders for is, like, they take a single point geometry vertex and then compute a quad from that, or like a polygon that is more complicated than a single point. So this would be typical things that you would perform in a geometry shader. And then there are also tessellation shaders to approximate curves using subdivision surfaces and Bezier patches. They're more shaded type, but they're not so important to us. What are the shaders that are most important to us for our understanding also of how architectures work nowadays and how those architectures actually came to being are the vertex and the fragment shaders. And we now have an understanding how those shaders work, what they do, what they are there for, and that should be enough for our purposes. So with OpenGL, we have a model where the shaders are actually compiled and linked at runtime. That is, when we compiled the whole OpenGL program, the shaders are embedded as basically as strings, like as text. And then the OpenGL library basically includes with its runtime a compiler and linker. And the compiler and linker will take the shader source code and will compile it, and will link the compiled output into a shader program. And that shader program can later be used. Like, we'll really have to create the shader, the vertex shader, and the fragment shader from source. Like, we'll take a vertex shader string, which is actually the real GLSL program code, and then we compile it. And we do the same thing with the fragment shader. And then we create a program and we attach the two shaders to it, like the vertex shader and the fragment shader, and then we link that program and then we use it. And that, of course, is actually quite error prone. And there's, of course, some runtime overhead, which can, like, when you have a very shader heavy program, like a computer game, for instance, which can actually be quite significant, that you have high load times on program start. But what is actually quite error prone is that different OpenGL implementations, like the Microsoft Windows implementation or the Linux implementation or the macOS implementation, they actually interpret the language quite differently. So, and the problem here is really that you usually have to really make sure that your program is compiled in the same way and without errors for all IHVs that you want to support. And this can actually be quite difficult, and the problem here is that this actually happens on the user side. So it's nothing that the application developer can catch when they compile the program, but it actually happens on the side of the user. So newer APIs, like for instance Vulkan, or DirectX had this from the beginning as far as I know, but Vulkan has an intermediate representation. This is called the SPIR-V intermediate language. And this intermediate representation is much more similar to the actual machine code that is executed on the GPU. So the compiler would only have to interpret that intermediate representation. So we would, at compile time, compile our program into the intermediate representation, and the runtime would ship a compiler that runs over the intermediate representation and turns that into machine code. And this actually turns out to be less error prone, and also we don't need to like obfuscate the code, because like when the code is actually embedded into the binary as a text object, then it's also easy to obtain that text object like using a hex editor. And this can obviously also be problematic, like when we have like some certain logic stored inside the shaders that isn't meant for the outside world, or that you don't want to open up so that everyone can view what's happening in our shaders. With legacy graphics APIs, there's this feature that I actually mentioned a bit earlier, which is the so-called matrix stack. And the matrix stack is actually part of a hierarchical design that many of the legacy APIs followed. And OpenGL, for instance, also had that. And I want to really briefly just sketch the idea behind those hierarchical APIs. Like, imagine we're having a geometry like this here. Like we're having this robot or humanoid or whatever that is. And so the robot has like a couple degrees of freedom when it comes to movement. Like the robot can move forward, like can move straight ahead. And this is expressed via this translation T here. And at the same time, the robot can also like rotate its arms. Like the robot is able to rotate the right arm around this axis here. And the robot is also able to rotate the other arm like around the same axis. And this basically forms a hierarchy. Like when the robot moves and at the same time the arm moves, then the rotation can be thought of hierarchically as a child of the translation. Because like obviously when the robot moves, the whole robot will move, and when the arm rotates, it will do that with respect to the axis, with the moving axis still being the origin of rotation. And so basically with the translation, the center of rotation for the two rotations moves. So this basically forms a hierarchy, and this hierarchy is what people would call a scene graph. Like scene graphs are usually more complex than this. Like this is the most simple scene graph I could personally imagine. But the scene graph allows us to express a rather complex transformation and rather complex movements. And if we were to like render this with a legacy API, we would use what is called the matrix stack. And the matrix stack would work as follows. Like we have this stack data structure here, and the stack would initially be empty, and then we would issue a command, and the command would instruct our graphics API to push the translation on the stack, right? So now we have the translation on the stack, and then we would draw any geometry that is subject to the translation, but only to the translation. Like we would draw the robot's body, and we would draw the robot's head. And by drawing them, we would like transform the vertices with the translation on the stack. So we would then next, like we would traverse this hierarchy, like this scene graph, and we would traverse this in some order that is predefined by our application. Like, and our application might just decide to traverse the scene graph in pre-order. So we would next push the left rotation on the stack, and would then draw all the geometry that is subject to both the translation, which is still on the stack, and which is also subject to the left rotation. Like this would just be the left arm, and then we would draw this left arm here. And that would be all the geometry that is subject to those two combined transformations here, which together like form a single matrix. And as this is the only geometry that is subject to this transformation, we would then pop the transformation from the stack. So the stack would now again only contain the translation. And we would then traverse the hierarchy to eventually arrive at the other rotation, like in the rotation for the right arm. And so we would push the rotation for the right arm on the stack, and then we would draw the geometry that is subject to this rotation, which would just be the right arm. And with that we were finished, like the whole robot was drawn. And then we would just pop all transformations that are currently on the stack, we would just pop them so that the stack eventually is empty. And then in the end, we would just present the image. So what we're basically doing here is we are using a stack data structure to traverse a tree. Like usually tree traversal is a recursive routine, and we're using a stack data structure to accomplish traversal through the tree and to accumulate the relevant matrices here. And older graphics APIs, like for instance OpenGL, would support such a mode where you could just push transformations to the stack. And then whenever you would issue a draw call, the vertex positions, they would be subjected to the current accumulated matrix transform. And then the APIs would have driven transforms for projection and for model view. And like as a matter of fact, this type of API is nowadays considered like legacy mode. Like newer OpenGL versions don't support this anymore. And one can speculate about the reasons for this. But I have a feeling that many applications actually internally maintained their own matrix state and their own tree traversals, and then also maintained their own camera matrices. And that eventually resulted in lots of redundancy, and so that nowadays APIs are like shader based, and the application is just assumed to pass those camera matrices into the shaders itself and like compute what the relevant camera matrices would be. But this is just the basic principle behind a hierarchical matrix stack based API, like OpenGL was in the very early days. So those hierarchical pipelines were something that's quite typical for older APIs like OpenGL in older versions and Direct3D in older versions. And there were hierarchical pipelines not only for the matrix stacks or for the transformations, but also for attributes. And like nowadays, it's kind of assumed that the application maintains that hierarchical state itself. And quite often, this is just done using some sort of scene graph library that operates like on top of the low-level graphics API. And the interoperability between those libraries and the graphics API is basically by passing matrix transformations and by passing state as uniform variables to the shaders. But what should be noted is that there's still lots of legacy OpenGL code out there, and that also has to do with like the deprecation mechanism of OpenGL. Like even today, it is perfectly valid on all relevant OSs to write OpenGL 1.2 code or 2.0 code that uses all those features, like uses the matrix stack, uses immediate mode, geometry specification, and all that. And all those features are still supported by the OSs. And presumably, that has to do with a relatively slow extension mechanism that OpenGL employs, and that also includes a relatively slow deprecation mechanism. Like when we compare that, for instance, to the Direct3D and DirectX API by Microsoft, we see that Microsoft pretty much controls everything, like decides, for instance, that a API is deprecated and then completely redesigns it from the ground up. Like for instance, Direct3D 12 was a complete rewrite of the API and was completely different than the API before. And in contrast to that, like OpenGL has a extension mechanism where the vendors start proposing an extension, and then they are in this mode where they are a vendor-specific extension that is developed against a certain OpenGL standard, and they can be identified by those prefixes that show us who the vendor is actually. And from there on, like certain vendors might agree that an extension is there to stay, and then it gets this prefix X'd, and only then, after some time, the extension is really taken under consideration, like by the architecture review board, by the ARB, and then, only then, it is discussed if the extension should be included in a future standard. And when it's in this state, like that it's an ARB extension, then there are some chances that it will like eventually even become part of the core profile. But like, you can already see that this is a very slow and a very sluggish process actually, compared to a process where not a consortium, like an industry consortium, but rather a single company, like for instance Microsoft, decides about the fate of the API. And the deprecation mechanism is actually quite similar. On the other hand, this is of course also a very flexible mechanism. Like when a specific vendor decides to include an extension, this is relatively easy. Like the extension is just there, and the application developer would load the functionality that is associated with the extension using a function pointer. Like the function pointer would be initialized by the API. And if the extension is just not available, like because we're on an architecture from a different vendor or because we're on an older architecture, then the function pointer initialization will just fail. The function pointer will become a null pointer, and we can thus easily check if the extension is available or not. So the mechanism is actually quite flexible. So if a vendor decides to add a certain feature, it's actually pretty easy for them to add that feature. Only that this feature then isn't like fully and officially supported, and until it really gets fully supported and fully maintained by the consortium, it usually takes like a lot of time. And deprecation has a very similar dynamic actually. So and that was our brief tour of the OpenGL API. So this was really not meant as a tutorial, but it was basically focused on showing how those legacy APIs work, how they evolved, and it also helped us to understand certain terminology. Like for instance, we now know what a shader program is, we know what an OpenGL context is. When I'm talking about the OpenGL matrix stack, you know what I mean by that. So it's important for us to get the terminology straight, and those older graphics APIs actually determine much of the terminology that is used when you talk about GPU architectures. So I propose that we finish today's session with a bit of a more relaxed topic. Like we're going to discuss the historical development of graphics processors. Now that we've already talked legacy graphics APIs, this should be the perfect ending to this session. And we will start what was in the early 2000s was called the graphic processor. And those were the very first processors where the graphics actually weren't performed on the CPU. Like before that, we had those huge SGI graphics workstations, with SGI mostly being targeted at more serious applications, like for engineering, for example. But SGI also was known, for instance, for their cooperation with Nintendo on the Nintendo 64, for instance. And SGI was actually a global player, and they did 3D graphics on CPUs, on dedicated CPUs. And then in the late 90s, early 2000s, those graphics processors became quite popular, and notably the 3DFX Voodoo and Voodoo 2 cards, and NVIDIA's Riva TNT cards. And then later those were superseded by the very first GPUs, which was like a marketing name that NVIDIA invented. And then later the architectures actually evolved quite a bit until they became what they are nowadays. And we will only very briefly discuss those developments. And we will put those developments in perspective by observing which part of the graphics pipeline was implemented on those devices and how those parts were actually implemented. And the graphics pipeline should actually look familiar to you because it's really the algorithm Rasterization 2, but in disguise. So it's really the very same algorithm that we discussed over and over again during the lecture. Like we have vertex specification, which is basically the user providing input. And then we have vertex processing, which is the vertex phase or the vertex stage that we discussed. This is followed by primitive assembly, where the primitives, the specified primitives, were clipped against the view frustum and new primitives were created. And that is followed by scan conversion that takes the edge equations from the primitive assembly phase and turns the edge equations into fragments. And fragment processing is basically comprised of shading and lighting those fragments. And then in the end, we have the, like what I call the per sample operations here, or what I sometimes also call the ROP operations or the raster output operations. Like this is basically blend and the depth test, and this happens on a per sample basis. And so the very first graphics processors in around 1996-97, like the Voodoo 2, for instance, by 3DFX, they performed the whole vertex processing phase on the CPU. So the whole vertex processing phase was CPU side. And there were like APIs like the Glide API that could be used to program those coprocessors. And then after vertex processing, the actual graphics pipeline would be executed on the device. Like the transformed vertices would be passed to the graphics accelerator, and there the rasterization algorithm would be performed, like starting with the primitive assembly phase. You can already see that the device consisted of like a bunch of different chips, most notably like dedicated texture management units, like dedicated chips that would perform texture, address mode resolution, and interpolation. So, and the names of those chips, I mean, if you like to watch movies, they might sound familiar, I don't know. And around 1999, like the first GPUs were introduced, like what NVIDIA called a GPU, a graphics processing unit. So in the marketing slogan was that the GeForce 256 was the first hardware transformer lighting engine. That is, the GPU was able to perform both the transform phase, like the vertex transform phase, and the lighting phase on the device. And a couple of years later, NVIDIA pushed the GeForce 6 series GPUs to market. And that actually marked the advent of programmable shaders and was quite a different architecture compared to the GPU architectures from before. And when we have a closer look at that architecture, we see that there's a dedicated bunch of vertex and fragment processors, and we have that streamlined pipeline-like design where the vertex processors would process the user input, and then the vertices would go through the cull and clipping phase, like through the vertex setup phase, and that would be followed by scan conversion, and the output from scan conversion would be fragments that would go through the fragment processors. So we have this design where we have dedicated processors for the vertex phase and for the fragment phase. So if we actually have a closer look at those processors, we see that they had a very particular design. Like the vertex processor, for instance, would have a dedicated unit for vector of 4 floating point numbers, and for operating on those, like which would be typical for homogeneous coordinates. And then there were dedicated units, for instance, for primitive assembly. And the fragment processors also had a pretty particular design with a particular floating point processor arrangement with a fog ALU that would only make sense for a fragment processor. And the design was already pretty much centered around hiding texture access latency, like when those fragment processors access image textures, then they would hide the relatively high latency from that and would at the same time perform computations. So those units were actually designed to hide floating point operations behind texture fetches, which is actually a common theme up until today. So in those particular designs, which leads to load imbalances. So like if we had our processors, like the vertex processors, working on a very large number of vertices, and in contrast to that, the number of generated fragments was relatively low, then we would have a load imbalance where the fragment processors would starve. And on the other hand, we could have similar load imbalances if we only had very few vertices and a relatively high screen resolution or a spatial arrangement that resulted in many fragments. So there are actually certain recommendations as of how to balance those loads. It was generally agreed upon that one would specify relatively few triangles so that the load could be balanced on the user side. But only a couple of years later, that led to a architecture that is nowadays called the so-called unified shader architecture. And with this architecture that was introduced around 2007 with the G80 NVIDIA chipset, we saw one processor type that could perform the same operations, that is the transform and the lighting operations. And that means that if we had a relatively high vertex load, then we could dedicate some of the processors that would otherwise process fragments to the vertex operations, and vice versa. If we had more fragments than vertices, then we would just dedicate more processors to fragment processing and thus resolve the load imbalances. And that actually helped quite a lot with the load imbalances, and actually shaped the design of current day's GPU architectures quite a bit. And the principle behind that was called like unified shader architectures or unified shader cores. And this architecture actually, like a state machine as we discussed it during our tour through OpenGL, paired with a unified shader architecture that can, on the vertex and on the fragment stage, perform all the required operations, will be the topic of our architecture session, where we explore how triangles would be rendered and transformed into fragments and into vertices based on current day architectures. So, in the very first architecture that actually implemented that was the so-called G80 architecture, like the GeForce 8800. And it was like around 2007. And the design underlying this architecture was one where we had those unified shader cores, and each of those unified shader cores would have access to a shared L2 and would eventually also have access to the frame buffer. And each unified shader core on its own would consist of an array of so-called streaming processors, where each streaming processor can be thought of as like a tiny lightweight processor core with different characteristics than a typical CPU core, but still. And we had a relatively high number of those tiny cores. And then there were dedicated units for texture accesses. Like on the one hand, there were texture address units, which take care of texture address resolution. Like when we access our texture with texture coordinates, and we're maybe accessing the texture out of range, then there are certain ways to handle that, like to resolve the out of range access by either wrapping around or by assigning a constant border color, for instance. And we had a dedicated unit to which would basically be concerned with texture coordinates. And then there was another unit that was concerned with texture filtering, which would imply, like for instance, bilinear filtering in the texture image. And the design was a streaming design in a fashion that there was complete overlap between the processors that were concerned with compute and the processors that were concerned with memory accesses. And then those unified shader cores had and also have nowadays a shared L1 cache that our cores can access. And those architectures actually evolved quite a bit. When we discuss newer architectures like we have them today, we'll, for instance, also find a dedicated memory region that is called the shared memory that actually has pretty similar characteristics to the L1 cache, but can be accessed from within the shader cores, even programmatically. We will talk about this when we discuss CUDA, when we discuss GPU. But those are the typical characteristics of the unified shader cores that were introduced around 2007 and that later found their way into architectures that supported GPU with APIs like NVIDIA's CUDA. So then eventually with the Fermi architecture, GPUs even gained full double precision support, which is actually quite important when you, for instance, want to perform physical simulations on a GPU. And another performance-critical thing that was introduced with the Fermi architecture was support for so-called fused multiply-add, which basically performs the operation multiplication and addition in a single instruction, which is actually quite helpful because this is, for instance, the core operation that is performed when we compute convolutions or when we compute interpolation, etc. And so the Fermi architecture was actually a pretty powerful architecture and made actually quite a jump in performance because of the scheduler that the architecture shipped with. When we run a program on this unified shader core, there needs to be some management how threads are scheduled on those cores. And the scheduler with this architecture actually improved quite a bit. And therefore, the Fermi architecture actually made quite a jump in performance with respect to the previous generation of GPUs. And based on those considerations, we have a better understanding of how GPUs evolved into what they are today. And based on that discussion, we can now also better understand how current GPU architectures work. And this is what we'll look into throughout the next sessions.